Today we're going to do 4.5, the dimension of a vector space. Theorem 10, if a vector space V has a basis of n vectors, then every basis of V must consist of n vectors. Suppose B1 is a basis for V of exactly n vectors. Suppose B2 is another basis for V. By definition of a basis, we know that B1 and B2 are both linearly independent sets. By Theorem 9, if B1 has more vectors than B2, then B1 is a linearly dependent set, which cannot be the case. Again, by Theorem 9, if B2 has more vectors than B1, then B2 is a linearly dependent set, which cannot be the case. Therefore, B2 has exactly n vectors also. Finite and infinite dimensional. If V is spanned by a finite set, then V is said to be finite dimensional, and the dimension of V, written as DIMV, is the number of vectors in the basis for V. The dimension of the zero vector space 0 is defined to be 0. If V is not spanned by a finite set, then V is said to be infinite dimensional. In general, the dimension of Pn equals n plus 1. Therefore, the basis for P3, P1, P2, P3, which is 1t and t squared, so the dimension of P2 would be 3. Let's look at example 2. And yes, we're skipping example 1. I took it out years ago. So example 2, find a basis in the dimension of the subspace. So the first thing we're going to do is we're going to write our matrix in terms of 4 vectors. So we're going to take and write A plus B plus 2C, and then 2A plus 2B plus 4C plus D, and then B plus C plus D, and then 3A plus 3C plus D. And we're going to write this in terms of A, B, C, and D. So A would be 1, 2, 0, 3 plus B times 1, 2, 1, 0 plus C times 2, 4, 1, 3 plus D times 0, 1, 1, and 1. We're going to call these vectors V1, V2, and V3, and V4. So W equals the span of V1, V2, V3, and V4, where V1 equals 1, 2, 0, 3, V2 equals 1, 2, 1, 0, V3 equals 2, 4, 1, 3, and V4 equals 0, 1, 1, and 1. We can discard V3 since it's a linear combination of V1 and V2. So by the, and that's by the span and set theorem. And we can, V4 is not a linear combination of V1 and V2. So V1, V2, and V4 is the basis for W. Therefore, the dimension of W equals 3, since we can discard V3. Let's look at the dimensions of subspaces of R3. So the zero-dimensional subspace contains only the zero vector. The one-dimensional subspace span V, where V does not equal 0 in R3. These subspaces are lines through the origin. The two-dimensional subspace span U and V, where vector U and vector V are in R3 and are not multiples of each other. These subspaces are planes through the origin. And then three-dimensional subspace span U, V, W, where vector U, vector V, vector W are linearly independent vectors in R3. The subspace of R3 itself becomes the columns of A, U, V, W, span R3 according to the invertible matrix theorem. Theorem 11 states, let H be a subspace of a finite dimensional vector space V. Any linearly independent set in H can be expanded, if necessary, to a basis for H. Also, H is finite dimensional, and the dimension of H is less than or equal to the dimension of V. So to show that we can let H equal this span here, then H is a subspace of R3, and the dimension of H is less than or equal to the dimension of R3. We could expand the span and set 1, 0, 0, 1, 1, 0 to 1, 0, 0, 1, 1, 0, 0, 0, 1 to form a basis for R3. Theorem 12, the basis theorem, let V be a p-dimensional vector in space p greater than or equal to 1. Any linearly independent set of exactly p vectors in V is automatically a basis for V. Any set of exactly p vectors that spans V is automatically a basis for V. The set of p elements, so we have the set of p elements, the dimension of V equals p. Example 3, show that T, 1 minus T, 1 plus T minus T squared is a basis for P2. So we're going to let V1 equal T, V2 equal 1 minus T, and V3 equal 1 plus T minus T squared. And B equal 1 T and T squared. So we're going to write our corresponding coordinate vectors. So our coordinate vector V1 of B is 0, 1, 0. Our coordinate vector of V2 on B is 1, negative 1, 0. And our third one is 1, 1, negative 1. And our second coordinate vector is not a multiple of our first one. And our third one is not a linear combination of the first two. Therefore, our three corresponding coordinate vectors are linearly independent. And therefore, our vectors are also linearly independent. Since the dimension of P2 equals 3, V1, V2, and V3 is a basis for P2 according to the basis theorem. So let's look at example 4. Suppose A is 1, 2, 3, 4, 2, 4, 7, 8. Find the dimension of A and the dimension of null A. So we're talking about the dimensions of column A and null A. So you need to remember that column A is determined by the pivots columns of A, and the dimension of null A is determined by the free variables. So we have to do that for both of these. So first, let's find the dimensions of column A. And when I row reduce this, I can take negative 2 row 1 and add it to row 2 and get and these are my pivot columns right here and right here are my pivot columns. So one, 2, because that's the column where I have a pivot, and 3, 7 is a basis. For column A. And the dimensions of column A is 2. So we found our dimensions of column A, which is 2. Now we need to find the dimensions of null A, and remember that's the number of free variables. So we have to solve for AX equals 0. So when I do that, I get 1, 2, 0, 4, 0, and 0, 0, 1, 0, 0. So x1 would equal negative 2x2 minus 4x4, I believe. x2 is free. x3 would equal 0. and x4 is free. So going over here, x1, x2, x3, x4 would equal x2 times negative 2, 1, 0, 0 plus x4 times negative 4, 0, 0, 1. So negative 2, 1, 0, 0 and negative 4, 0, 0, 1 is a basis for null A. And the dimension of null A is 2. So two things you need to remember. So note that the dimension of column A is the number of pivot columns in A, and the dimension of null A is the number of free variables in A.